In infrared spectroscopy, a sample is irradiated with polychromatic infrared electromagnetic radiation. As a result, some of this radiation is absorbed by the material, and by studying the spectrum of the transmitted radiation, it is possible to obtain information about the substrate that we want to study. Anyhow, there is a reason why the radiation gets absorbed by the studied substrate. Namely, if the exciting electromagnetic radiation has a specific amount of energy, then it can be transferred to a molecule and cause it to vibrate in a unique way. Note that a different wavelength exciting radiation is required to initiate each of these vibrations. In a real measurement, it means that when we compare the spectrums of the exciting radiation and the transmitted radiation, then we see that in the case of the radiation that has passed through the substrate, the intensity at certain wavelengths or wave numbers has significantly dropped. That's because at those wavelengths the radiation was absorbed, causing a specific vibration. The system consists of a radiation source, a beam splitter, two mirrors, and a photodetector. Depending on the setup, the sample is normally placed in front of the detector. And here's how it works. When the monochromatic infrared radiation that was emitted from the source reaches the splitter, which is basically a partially transparent mirror, then some of the radiation passes through the splitter, while the other part is reflected. These two beams then reach the mirrors, where they are reflected back towards the splitter. At the splitter, both beams are split again, causing a part of the radiation reflected from the fixed and moving mirrors to recombine and go through the sample into the detector. The other part of the radiation that was reflected by the mirrors, however, goes back to the radiation source. Currently, both mirrors are set at an equal distance from the splitter, and this causes the two beams reaching the detector to be in the same phase. That's what we call a constructive interference. At this point, the radiation reaching the detector has the highest intensity. However, if one of the mirrors is moved by a short distance, then the intensity of the radiation reaching the detector suddenly drops. This is because the two recombined beams are no longer in the same phase and cancel each other out. That's what we call a destructive interference. So, in order to carry out the measurement, the mirror is moved from point A to B, and as a result we get an interferogram by measuring the intensity of the radiation that reaches the detector. This interferogram can then be converted into a spectrum through a process known as Fourier transform. As mentioned earlier, in a real experiment we use polychromatic infrared radiation, which means that it consists of many different wavelengths. This also causes the measured interferogram to be somewhat more sophisticated, but for a modern computer it is not a program to convert it into a spectrum.